15.4, 15.5, 15.6, double integrals, applications thereof, and triple integrals. What questions do you have for me?
22.
22.
Can you just set up in?
Okay. So we've got a cylinder. You said 22, right?
Yes.
It's that third one that's the pain in the neck to me. But let's see if we can start this. You want to do it with a picture or without? Okay. So my first reaction is, hey, that's an equation in 2 variables. That's an equation in 2 variables. I don't have any equations in 3 variables, but they said cylinder. And cylinder means to me a free parameter. So my first reaction is that should be the one I start with because that'll go in all x's. There's no x in that equation, right? Oh, sorry, no y's. It'll go in all y's. So x squared plus z squared equals 4. What's that a graph of? Right? But what's the cross section of that cylinder? Long ways it's this way, yeah, in the y direction. What's the other part of it look like? Just a circle. It's a circle of radius 2 centered at the origin. That's in the xz plane. And we should go that way with this, right? As far as we want. Except that we're limited in our y direction. Here. Y equals -1. So we can only go back that far. What about this? It's all first power, so that's a plane. And it's got no x's, so it'll basically be whatever line I draw in y and z. And then it'll go in all the x direction. So let me think about that. Y plus z equals 4 is the same as z equals -y plus 4, right? So in the zy plane, we have a z-intercept of 4 and a slope of -1. So I need you to think about the cylinder. So I'm going to try and draw that cutoff. Right? We go out in the y direction. And then when we cut off a plane. So we'll end up with some oval here. And we have another circle back here. So the circle on the left end and this oval on the right end. Okay, wait a minute. Those are boundaries in Y. So right away, I'm thinking of this as having a left and a right, rather than a top and a bottom or a front and a back. So I'm going to start with Y is between -1 and, oh, wait a minute. -Z plus 4. There's a left and right. So I'm going to do this dy first. And then we're going to do dx dz. So let me just think about the xz part of this. If I'm standing at this end and looking this way, what shape do I see? Circle of radius 2 centered at the origin. Now, you have a choice. How do you want to describe that region? Okay, but now I have a problem. This is an x and z, not x and y. So if I want to do polar, one of those has to be a z, not a y. I can do that switch, that's fine. I can say, okay, well then I'll let x equal r cosine theta, and I'll let z equal r sine theta. That's perfectly fine. Because once I do this integral with the y part, there will only be x's and z's. I can switch polar then. I'm just twisting my polar a little bit so that it lines up with the axes I've got. What are the boundaries for r and theta?
0 to 2.
And theta?
0 to 2.
Because I go all the way around the circle. Ta-da!
Simplify it using dy first.
Yeah. Yeah, when I do this integral, we're just trying to find the volume, right? Is that what the problem says? Find the volume? Then what are we integrating? What goes here? Ah, very last thing I said in class on Monday. Exactly. Integrating one when it's flat is linear. Integrating one when it's a shape is uniform. This is not the only way to do this problem. There are others. It's much more difficult to do this in x and z, because you'd have to write the equation for the circle. Well, we have it, x squared plus z squared equals 4. You'd have to write it as x equals top and bottom, that's right, right and left. Or you'd have to write it as Z equals top and bottom. Do that as either type 1 or type 2. Much easier to do a circle and pole. Mia, does the way I made the region make sense?
Mhm.
Okay. More questions. More stuff. Oh, and you could graph all of that in graph. Get a better picture than my POS. Question 10, 15. Find mass, center of mass for the lamina with the given density and the given boundaries. D is enclosed by y equals 0, y equals cosine x. X is between negative pi over 2 and pi over 2. And our density function is y. So, first thing I'm going to do is ask you to draw me a picture. What's the graph of cosine from negative pi over 2 to pi over 2? Aha. Now, I don't know what the mass is. I need to figure out the mass and the moments. Mass is the integral over the domain y, because y is our density. The moment in x is x times the density. And the moment in y, wait, I've done that backwards. I always screw this up. The moment in x is y times the density, right? We're measuring what x it's going to swing around. So we integrate with respect to y. I always have to go look these up. This is why we have the formula sheets. mx. I'll write the name first. No, mx is the double integral of y. That is correct. And y is the double integral x. Page 1018. X bar has my, there's the x times mx, there's the y times. I'm glad we get a note card. Okay. Please note, my density only depends on the y value. So this thing is very light at this edge and very heavy up here, right? How about left to right? Density doesn't change as we go left to right. Where should the balance point of this thing be? Somewhere in the middle, right? So I'm already going to make the assumption that the moment that I use here should work out to be 0. That way we'll be in the middle. I don't know how high we'll be, but we'll be in the middle, left to right. So x bar, my over m, y bar, mx over m. I gotta do 3 integrals. So let's do that first integral. First question, before I actually do either of the integrals, these integrals are all dA. Do you want to do this as type 1 or type 2? dy dx or dx dy? Because I've got a curve on the top and a curve on the bottom, and a number on the left and a number on the right. So I'm going to write my boundary. Y is between 0 and cosine of x, and x is between minus pi over 2 and pi over 2. There you go. Set up and compute 3 integrals. Compute the ratios, and you found the center of mass. I hope I'm right that x bar is 0. And y should work out to be 0. But I haven't worked it out yet.
Are you able to do this on the phone?
No, that's not a circle.
Oh,
It's part of the cosine curve, right? It's not actually a circle. I could try, but then writing y equals cosine x in r and theta is going to suck. I don't want to do that. Make more sense? If the density was 1, I'd call this a centroid instead of a center of mass. It's the only time we use the word centroid is when the density function is 1. And because we were talking about centers of mass, and because this was the thing that I recorded, I didn't get to record it before the baseball season started. Tell me about a torpedo bat. The New York Yankees hit 9 home runs in their opening game, 3 in the first 3 at bats in the first inning. All they did was move the center of mass of the bat. That's it. Instead of looking like a cylinder that gets wider and then is solid, that gets a little bit bigger and then gets back down to size. It's still solid wood, it's still smaller than regulation diameter. They just moved the mass in from the end. I put the mass right in the sweet spot where they swing it, and they customized it to every individual bat based on the way they swing. The bats are barely visually different. 9 home runs in one game. 3 up, 3 out of the park. Amazing. Center mass. For real. Anyhow, no practical application of this. It's completely a theoretical course. We never use this anywhere. More questions?
the 15, 12.
I hope so. 15,412. Find the center of mass in 11 if the density at any point is proportional to the square of the distance from the origin. Okay, wait a minute. What's our lamina in number 11? What's our shape?
Circle.
The whole circle?
Oh.
Okay, the first quadrant. Which radius? What's the radius of the circle? Okay, so now the question is, how do I write the density equation? Because once I have the density equation, I know how to do all the rest of this, right? So what is my density equation? What do they tell me? That's in 11. What does it tell me in 12?
Is proportional.
Proportional means there's some constant K. I don't know what it is. Distance from the, okay, so let's pick a point. How far is this point from the origin? That's not all right. What's the distance between 2 points? Oh, if I know the coordinates of this point are x, y, then the distance from the point to the origin that's the distance formula. Well, I'm going to square that. What's going to happen? I have my density function now. A density that is small in the middle and more concentrated as we go out. I don't know. Maybe an s orbital. If I did it in 3D, it would be an s orbital. Ladies and gentlemen, pick the right K. I give you quantum. But now, looking at this region, looking at these integrals, now I say to myself, this is probably better in point. Yep. So notice that what's going to happen in each of these integrals, I'm going to get a K, right? So I get a K when I do the mass, and I get a K when I do the moment. But then when I do X bar, I'm going to have a K on top and a K on the bottom. It's going to cancel out. When I do Y bar, I'm going to get a K on the top and a K on the bottom. It's going to cancel. Now, again, let me ask a question strictly by symmetry. Where should this sucker balance? If it gets heavier as it goes out, do you care about how far to the left or the right I am? So it should balance in the middle, in angle, which means it should balance on the line y equals x, which means if I do it right, x bar and y bar should be the same number. Should it be closer to the origin or closer to the edge? Which is heavier? So if the edge is heavier, it should be closer to the edge to balance. Light on one end, heavy on the other, I'm going to have to balance closer to the heavy end. My baseball bat problem again. That's clearly light on the handle end and heavy on the outer end. The balancing point for the center is closer to the outer end. I left my baseball bat at home.
What did they do?
Hmm?
What did they do?
Baseball bat? They made the baseball bat, instead of coming out and tapering and going straight, they made it bulge out a little and then taper in. So it looks like a torpedo in the water. And that bulge in the middle is right at the sweet spot of the bat. So there's more weight right behind where that battery wants to be. And therefore, they knock it out of the park fast. 9 home runs in one game. Ridiculous. Hmm? It is the record. Considering the opening game Friday against the Yankees, yeah, we're in deep. In a cricket bat, you've got that back curve, right? The front is flat, but then you flex. So imagine shifting where the weight of that curve is to be a little lower down if somebody hits low bowls. That's supposed to be higher for somebody who hits high bowls. Because bowlers can vary so dramatically, you don't always try and hit in the same spot. So most of it is uniform. Same idea. If I could dynamically figure where the bowler was going to throw most often, where I was going to hit most often, I could put more of the weight of the bat there. Dr. Mahady sent me an email yesterday about this because the statistics were off the charts with what they did. And so I had to look into it. I'm like, oh, this is this class. I have to tell you people about this. More questions. Ask me more stuff. I don't know, Nora, what will you get for on that? I think it will be at home.
No.
Yes.
For 15.6, it's just like a jumble of A's and B's. How much do we have to simplify that for like the X bar and like,
Oh, 15, wait, 15.4.6?
yeah.
Oh, I think you wrote down the region for 4.
Let's do that.
Yeah, the region for 4 has A's and B's in it. The region for 6 is a triangle. That's okay. I was like, wait, A's and B's. I'm looking at the wrong problem. Oh no, there it is. On the other hand, using the A and the B actually is a more generalized version of the problem because it then says I can do it on any rectangle in the first quadrant, right? From 0 to A and from 0 to B. I like that. More generalized version of a problem allows me to do a little less work, even though I have to do it in variables in the first place. How much simplifying do you have to? That depends on how much the simplifying hurts. A distinct advantage is if it's the right answer, I don't care what it looks like. If it's the wrong answer, I need to figure out why it's wrong. Over in Lynch Hall, for example, on the board outside my office, I put a problem last month. And the problem was you have 2 equilateral triangles next to each other. They're touching at the base. The bases are parallel. Tops are the same height. Cross the lines from the midpoint to the opposite corner. How high is the crossing? And I drew a picture and I wrote above it, not to scale. Just priorities. I came in last week and Dr. Hoover had drawn it to scale and physically measured 3.5 centimeters each. And I'm like, that's pretty damn close because the right answer is 3.46 and 7,000 more decimal places, but that's pretty close. So if the answer is wrong, I need to know why it's wrong. I put a new problem up yesterday. Pretty sure all of you can solve that. 5. I'm gonna start with the first question. You've got a sphere. You want the part of the sphere above some surface, right? That's a top and a bottom. So I'm gonna do this DZDA. I don't even have to draw a picture to say, oh, I've got a top and a bottom above a plane. Part of the sphere, x squared plus y squared plus z squared equals 1. 1? 4. That lies above z equals 1. So I just said, wait a minute, I've got a ball. I'm cutting the top off. And now I can say to myself, I have a picture. I have a sphere. What's the radius of that sphere? Yes. So there's my sphere on the coordinate plane, but then I'm cutting it at a height of 1. When you cut a sphere, what shape do you get? Yeah, I'm going to get that little dome top, right? But its edge is going to be another circle, isn't it? Okay, so I want this thing. That's my section. And we want the surface area, right? So I'm going to have to set up that big square root. Double integral over some domain of this thing dA. I'll worry about that part later. For the moment, let me concentrate on the region. What's D? I think of this as a bottom and a top. I want the area of this little dome. I look down on it. What shape do I see? I see a circle. What circle? It's the circle that's made where these two intersect. So all I have to do is take the 1 and plug it in. What do I get? Now, I'm integrating on a circle. What's the easiest way to integrate on a circle? Okay, so I know later I'm going to do this in polar. What goes inside that square root? Unfortunately, no. Because we're asked for surface area. This is the piece that goes into the surface area equation. For what function? For the function that describes our surface. What's the equation f of x, y that describes my surface? What describes this little cap up here? This dome shape. Ooh, it's a yarmulke. Wash it, it shrinks up. My machine wash it. If I hand wash it, it's fine. So you need the partial with respect to X, you need the partial with respect to Y, you need to square them both. Yes, that's exactly correct. So let's figure out, how do we describe this in R and theta?
So it's just. It would just be 0 square root 3 0 2
I would write it all out in X and Y, do the conversions to polar, and that's then why I put in those limits. It is possible to rewrite that partial derivative equation to write it partial with respect to R and partial with respect to theta. But when we do that, things change. Because when we did it with the arc length, instead of getting df dr df d theta, we got r squared plus dr d theta squared. So I don't know how it would work in turning the f into polar. That would be much harder. So I'm much happier to do this all in X and Y first, and then just in one fell swoop go polar coordinates, change it all to R and theta, change the balance to R and theta. More questions? The part of the cylinder that lies above the square. Okay, the cylinder in question, what was the equation of the cylinder?
B squared.
Ah. And then what's the square? A rectangle? So that is a square. Which means that's that square. X goes from 0 to 1, Y goes from 0 to 1. Since that's a square, it doesn't matter whether we do this dx, dy, or dy, dx. They're all numbers. I got to do that same thing again. What's the function f that describes the piece I'm looking for? Because that would be what this is. If this is x and y, and the thing living above that is in z. So take that equation, rewrite it as equals. Perfect. Now I'm going to do the same thing we did up there. I'm going to take partial respect to x, partial respect to y, square it, plug it in, and go to 10. Excellent. Remember, it's what is the surface? And if I can describe the surface, this works perfect. And if I have the function z equals for my surface, that's f of x, y, that's what I want. In the long run, there are other ways to describe these surfaces as well. We're just not there yet. Bulged right there. It's bulged right there. Depends on where they put it. Yeah. Well, when you consider they broke the record, but they're not the only team using them. So, yeah, they set the record on their homeowners. Thought about that. The only other things I have experience with on centers of mass are things that are equally impractical. Fencing. Boomerangs. Bowling balls. Before Greg Barry came on in computer science, our former computer science instructor, Anastasia Turkry, and her husband were part of the bowling league in Greensburg. And it turns out that bowling balls have rather complicated centers of mass. They're not just spheres. Inside a bowling ball is an oddly shaped weight. Usually the weight is one side heavier than the other, so the ball spins in a particular fashion. I didn't know. Totally unaware of this. And it's only for the professionals or the larger, heavier balls. So it's only in the 13 through 16 pounds, so 6 to 8 kilos thrown down there and offset weird twists. Bizarre behavior. With fencing equipment, a standard foil is balanced 1 inch beyond the end of your finger. So if you've got that little bell right here, the balance point should be right. Like I said, in a weird. More questions. Ask me more things about our stuff before I wander off. Remember this problem for tomorrow. We'll come back to it. But we'll see you all then. I hope you have a wonderful rest of your day. Enjoy.